My name is Urmila Diwekar. I'm sorry I couldn't join you in person, and thanks to Zach that I could present this online. I am the president of a new startup called Stochastic Research Technologies LLC. We are doing a lot of research in developing novel adsorbents for removal of various contaminants from produced water like arsenic, norm, and also you can use the same technology for extracting valuable materials. The norm removal project has been funded by NSF phase 1 as well as phase 2 SBIR project. So we are now in the phase 2 of SBIR. In the phase 1, so what is our technology? In the phase 1, we developed novel adsorbents using a new approach based on computer-aided molecular design. So essentially what it involves is that we design novel adsorbents using everything on computer and then synthesize it in the lab. We concentrated on clay-based adsorbents because they are cheaper and easily disposable. So our project was actually first when we proposed was concentrated on radium, but in that project we also developed adsorbents for arsenic, barium, strontium, and radium. We have also now extended the technology to PFAS, and I'm not going to show all the results, but I'm going to show you something saying that this technology is versatile and can be used to design superior adsorbents for whatever you can have selective contaminants can be removed, as well as if you have valuable materials like lithium, you can extract that. We can customize the adsorbents for the situation. The concentrations are different in each well, produced water well. If you want to customize it, you can do that. And what we have seen that because these are designed to keep in mind the capacity of maximization, we find that these adsorbents are actually order of magnitude better capacity than current state of the art. And as I said earlier, they are clay-based, so they are cheaper, and especially when we consider disposal, so in terms of norm, the amount of waste generated is small, so even the disposal costs are order of magnitude lower. We are in phase 2. How we do it, I want to just briefly show the technology because it can be used for a lot of other things. So if you look at design of molecules, in general, people do it by doing experiments with different molecules and finding the best adsorbent, or just looking at databases. But what we are using is different, which is computer-aided molecular design. And I won't get into the theory of it, but essentially computer-aided molecular design is a reverse use of group contribution method. A molecule, suppose I have a known adsorbent and I have a property like adsorption capacity. If I can link this adsorption capacity to the groups of that molecule, I can say that each group of that molecule is contributing towards adsorption capacity, not only each group, the group interactions also. If I can have a group contribution model to predict the property from the groups, then what we do is we do the reverse of that, is we actually use combinatorial optimization to maximize adsorption capacity. Here I'm just going to show it for a solvent. Here is ethanol. So ethanol consists of three groups, CH3, CH2OH. The property of ethanol, so for example, if you are extracting the solvent, distribution coefficient can be linked to the groups CH3, CH2OH, and interactions of each group, like how CH3 is interacting with CH2 and all those. So there is a large scale thermodynamics model behind it. And essentially, if we can do the former, if I can predict the property from the groups, I can actually use combinatorial optimization method to select the groups and the molecule which can give me, which can enhance the property, maximizing adsorption capacity. So we use this approach. This approach, as I said, involves a lot of difficulties. It involves a lot of mathematics, and we combine thermodynamics and optimization to get to the problem. I won't get into the theory of it, but essentially, when we were looking at radium, we looked at current adsorbents. Since we were looking at clay adsorbents, we looked at clay adsorbents, which are currently removing radium. Their capacity was really very small. But what they had is the group values. So from this capacity correlations, we actually developed optimization algorithm, and we could generate very the different adsorbents for radium removal, and they are better adsorption. So we had done this, as I said, for arsenic, barium, strontium, and radium. And I can show you, and these are the experimental synthesis of this synthetic clay for each material. So A is for aerolite, which is arsenic adsorbent, barium, radium, and strontium adsorbent. They all have been tested in the lab with taking the Permian Basin water, produced water, not for arsenic. Arsenic, we did different experiments, but for barium, strontium, and radium, and they have done phenomenally well. I'll just give you an example of arsenic, because arsenic is something which we have a lot of data. These are the arsenic adsorbent in the table, which are currently available commercial adsorbent. Look at their capacity. It is 51, maximum capacity they can go is 51.3 milligram of arsenic per gram of adsorbent. Our adsorbent capacity is more than 10 times that. And this has been tested in the lab. So whatever we generated, we think they are working in real practice. For radium, we had taken water from Permian Basin. The concentration was varying from 1500 to 4000 picocuries per liter. And we actually did experiment with our adsorbent, and we found that actually 0.5 grams per liter adsorbent is sufficient to take out 95% of radium. Okay, so you can see that up to 1.5 gram per liter. So small quantities of adsorbent, but then you can also remove this. So this is for radium. If we look at the current radium removal system with barium sulfate, it had a really large volume of uh, actually waste is formed, which has to be discarded in nuclear waste sites, which can be very expensive. We did some techno-economic analysis, okay? We're considering our material, and what we found is that our material for a small portion of the market capture, we can reduce the cost of water treatment is 0.4, it's 45 cents per BBL. If we capture 0.1% of the market, that goes down to 5 cents per BBL. As compared to barite, that is 0.85 BBL. But if you look at waste disposal cost is reduced by 96%. Okay, this is for radium, and why I'm showing this technology for others also, because now what we are doing is we are using it for other materials. We started the project with theoretical results, NSF funding us. Phase 1, we showed that these adsorbents work for barium, arsenic, barium, strontium, and radium. And now we are in the phase 2. In phase 2, we have come up with, this is the conceptual diagram. Our adsorbent right now, we will be having a powder and essentially a stir tank with a filter. We are going to do pilot experiments in Bergendorf, maybe July or August, this August, to see how our adsorbents are doing with the high amount of produced water, also determining, optimizing the process and all those things. So one of the things I wanted to show you that what are we doing in phase 2 is we are actually optimizing the process design and operation. We have actually optimized certain steps in our design so that the cost can be reduced. We have completed the first draft of techno-economic analysis. As optimization does further, we will be updating that. Pilot plant experiments are planned at produced water site in Bergendorf. Most probably after all the permissions have come, we'll start it in August. We have actually been extending the technology to develop adsorbents for PFAS. And I think we are right now working on getting, theoretically at least, adsorbents for lithium, for extracting lithium from water. And we will then extend it to extracting rare earth elements from water. So this is the general outline. And one of the things I want to say is that ours is a startup, and we are looking for any guidance from you, is how you will be using this technology, what we should do so that you can use this technology in real practice. Mike is helping me in that, but I think any input is appreciated, as well as if you want to test our adsorbent in your facility, we can provide that too, because we have patented it. So we can provide you adsorbent to try out too. So with that, I want to thank you.